and thank you very much to be there, because as I said, it's absolutely not compulsory. So this last lecture will be more seminar-like than lecture-like, as I told you. So the official title for the lecture was Rotating Two-Dimensional Bose Gases, and the title of the seminar is Thermal Melting of a Vortex Lattice. So this is work that has been done in our lab in this bubble trap geometry I was mentioning earlier. And you will see a picture of the group at the end of this talk. So we are at the last part of the course. And as I said, now I change a lecture for seminar. Just a few words about our laboratory in France, which is called Laser Physics Laboratory. So it is in Paris, in the north of Paris, strictly speaking outside Paris, but it's in the big city. And there we have several groups who are doing experiments with cold atoms. Some of the experiments are with quantum gases, as I was mentioning in the course, so quantum degenerate gases. So there's a rubidium lab, sodium lab in my group, and there is also a chromium lab and a strontium lab. And then there are experiments with cold atoms, but not quantum degenerate gases. So another experiment with strontium is more about superradiance and aims at doing a clock with a superradiant beam of strontium atoms on a narrow line. There is an argon, a metastable argon lab who is looking at interferometry and the interactions between atoms and surfaces. And there is a lab with cold molecules. So for the moment, they are not so cold, but they are working in the direction of having cold molecules. And they use cryogeny. So they are really cold in the sense that there is a fridge at 4K. So these are the kind of things you can visit if you come to us in France. So if you are interested, you write an email to me. And if you pass by, you can have a tour of the labs. OK, so I will be quick in the introduction on why quantum gases are nice in general, because I told you that at the first lecture. The fact that you can take advantage of the great tunability of quantum gases. This one is an example where quantum gases are used to mimic quantum Hall physics, which is normally an effect in 2 dimensions for electrons. And in this particular experiment, they cheat a little bit, because the 2 dimensions they are using, one of them is a real dimension, so x, but the other dimension is in spin space. So the other dimension is because it's dysprosium atoms, and the dysprosium has 17 internal states. And so these 17 internal states, they treat them as 17 possible sites of like a fictitious position. And so there are 2 dimensions, are x and the spin. And so with this experiment, they were able to reproduce what is happening in the quantum Hall effect, where there, in a material, when you try to have a current going from the left to the right, what you observe is a potential difference between the 2 sides. And so there are either H states, bloop, 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 going on the side, or loops corresponding to the cyclotron motion in a magnetic field when you are in the bulk. So they observed this nice physics with cold atoms. So this is the spirit of what we call quantum simulation, mimicking other systems with well-controlled cold atoms. Then I discussed phase transitions, hydrodynamics, unconventional geometry like 1D gases or 2D gases. And what I will talk about is out of equilibrium dynamics in a bubble trap, where we are mostly in the 2-dimensional regime. OK, so this is a recap I already made a lecture on hydrodynamics and superfluidity. And the hydrodynamics equation, where there is a continuity equation and the Euler equation, they describe the collective modes. We have seen that. So this is a gallery of collective modes that we have observed in a 2D gas using principal component analysis. So this corresponds to the oscillation in one of the axes of the trap. This corresponds to the oscillation in the other direction. So these are the center of mass modes. This one corresponds to the scissors mode. This one corresponds to the monopole mode, and this was to the quadrupole mode. And this is all described by hydrodynamics. Also, the BEC expansion, if you release it from the trap, can be described by the hydrodynamic equation quite efficiently. And phonons, solitons, free particles, and quantized vortices. So I will really focus today on quantum vortices, and this is an example of the kind of things we can produce in the lab by rotating the cloud, as I explained, deformation, rotate the deformation, go back, and then the more you rotate and the more vortices you have, with a circulation h over m around each vortex. And so we do all this in this geometry. This is our trap, this bubble, which is relying on radio frequency field dressed atoms in a quadrupole magnetic trap. And in the presence of gravity, the atoms accumulate at the bottom of the trap. So if you're interested, I have also a full seminar on compensating for gravity, having atoms climbing on the side of on the edges of the bubble. But this is not for today, okay? All right, so this is what the kind of things that can be done in this kind of bubble. So I already mentioned the observation of the collective modes of the 2D gas, which sits at the bottom of the trap, the vortices. If you cut this bubble with an optical potential that confines the atoms to the equator of the bubble, so it cuts the bubble in the middle, such that the atoms must stay in a plane. So in this case, you produce a ring. So this is also something we did in the lab, but it is a hybrid trap with both magnetic, radio frequency, and optics. You can, by using two frequencies, have one bubble inside the other. And so it means you will have two oblate gases on top of each other. And with this geometry, you can do the kind of interference experiments to probe the BKT transition. And this is done in the group of Chris Foote. And I already commented this experiment yesterday. This is exactly the picture that you have seen shown by Raoul, but this is a colored version. So here, we rotate like mad. And the atoms, because of the centrifugal force, they climb on the edges. And seen from the top, you have this very nice dynamical ring, which is a ring only because it has angular momentum. Then there is no other trap, okay? It's not this situation. There is just a bubble plus a lot of angular momentum. And in fact, you can also produce a ring trap, so really a ring, by the bubble itself when you shake it vertically like that. Because if you take the bubble and you shake it quickly, the atoms cannot stay there because it's too much energy, unless at the equator. Because seen from the equator, when you shake vertically, it's tangential, so more or less nothing happens. And so the only place where the atoms can survive is the equator, and that's a way to produce a very thin and large ring and very smooth. And this is used in the group of Wolf and Klitzing in Crete to do some device that he uses for atom interferometry. All right, so this, what I will speak about today is this situation when we rotate and produce a vortex lattice. So this is the plan for this afternoon. After this introduction, I will describe how we rotate the atoms in the bubble, how it looks like, this vortex lattice. Then I will introduce you to the theory of what we expect, and then I will show you the results. Okay, so what's happening? So this is a lecture part. So this doesn't count for the seminar, we said. So we remove this type. Lecture part, what's happening when we set atoms in a rotating potential? So what I mean with that is imagine that the trap we use, that it is, let's say, a harmonic trap with two different axes. And we modulate some currents or field, anything, such that this trap in the laboratory frame rotates at some angular frequency, big omega. So it means that now the potential depends on time. It depends on time like that, with cosine omega t plus y sine omega t, etc. This is not very convenient to describe the physics in the Hamiltonian that rotates, because now we have a time-dependent Hamiltonian. And so the trick to solve this problem and to go back to a time-independent Hamiltonian is to look at what's happening in the rotating frame. So we make a unitary transformation with the unitary matrix e to the I omega t Lz over h bar. So you see that this is a matrix that describes a rotation by an angle omega t around the z-axis, because it is generated by Lz. Lz is a projection of the angular orbital momentum operator along z, and this is a generator for rotations. So if I now sandwich the Hamiltonian using this unitary transform, so I apply it both to psi and to u, what's happening is that my transformed psi obeys now a new Hamiltonian, which is the Hamiltonian in the rotating frame. And I can deduce it from the original time-dependent Hamiltonian by multiplying by u to the left, u dagger to the right, and adding this term that comes from the direct derivative of u. So this term, it is easy to compute because the time derivative is just having what is inside the exponential going down. So I omega Lz over h bar goes out. The two i's, they give a minus sign. The omega is here. The h bar is cancelled by my h bar here. And I am left with minus omega Lz. So the Hamiltonian in the rotating frame is just p squared over 2m plus now my potential, which of course does not depend on time anymore in the rotating frame. It rotates with the rotating frame. But it is corrected by minus omega Lz. So this is the expression of the Hamiltonian in the rotating frame. So Lz is xpy minus ypx. So I can let it like that Lz. When I look at the eigenstates for a harmonic oscillator, this is sometimes more convenient if the potential is rotational invariant to stay under the form Lz, because now I can find a basis in which both Lz and the Hamiltonian are diagonal. So the m states, which are the angular momentum state, are good quantum number. So I could let it that way. So sometimes I do that. But I could also replace Lz by its value in terms of xpy and ypx, and then recast this under another form that is very familiar. And here is what I find if I do that. So I can recognize that p squared plus some pxy, pyx, I can write it under the form of a translated p. So p is translated by some vector qa to the squared. So when I expand that, I find my p squared. And then I will have pqa terms and q squared s squared term. If I choose qa such that it is equal to m omega minus yex plus xey, I find the correct value with the Lz. But because of the q squared s squared here, I also have a term which is in squared of this value. And so square of this value is r squared, essentially. And in fact, what I find is that it will add to my potential 1/2 of m omega squared r squared. But then it will not be equal to the left part. So I have to remove what I have added here. And so the conclusion is that the Hamiltonian in the rotating frame is equivalent to the Hamiltonian we have for a charged particle with a charge q in a magnetic field B, which is equal to 2m omega over q, but corrected from this term that I have to remove to keep the same thing. And this is the centrifugal potential. So this term is the one that is responsible for the atoms to climb on the edge of the bubble. It is the one that says that in the rotating frame, I have the centrifugal force that pushes the atoms apart. OK, so this means, for example, if my potential is a harmonic trap potential, 1/2 of m omega r squared, that the effective trapping frequency is reduced. Because now, instead of omega r squared, I have omega r squared minus big omega squared. So it doesn't trap as much as before. And if I rotate so fast that the rotation frequency is equal to the trapping frequency, there is no trap anymore. So this would limit the rotation speed at which I can go. And so that's why, OK, this I forgot to mention. It is equivalent to having a magnetic field. So that's why there is an analogy between a quantum gas in rotation and superconductors, type 2 superconductors in the presence of a magnetic field that also have vortices. And the analogy with the physics of the quantum Hall effect. But the things I wanted to point is that there is this additional centrifugal potential. And so you can find a solution for this problem if your trap is not harmonic. But if the trap, in addition to some 1/2 of m omega r squared term, also has supplementary terms like quartic term or r to the 6 or anything that can help to hold the atoms at the point where the rotating frequency is equal to the trapping frequency. So if I did not have this, let's say, r to the 4 term, I would have something completely flat and the atoms would flow apart. But because the trap is harmonic plus quartic, I still have some trapping potential, even if I rotate at the trap frequency. And this is the case in the bubble, in fact. The bubble, you can rotate at the harmonic frequency, which is just an approximation at the bottom. Okay? It's a pendulum, the frequency in the bubble, so it's not harmonic. A pendulum is not harmonic. So there are some r to the 4th term that will help me keep the atoms. And I can even rotate faster than the trapping frequency. And in this case, I get the dynamical ring I have shown before. Dynamical ring is there when you rotate so fast that there is a maximum of potential in the middle and then a minimum at some finite radius r. OK, so this is how we can rotate very fast in the trap. And now let's see what it gives. So what we do is to start with a degenerate cloud at rest at the bottom of the bubble. So to give you an idea, the harmonic trapping frequency at the bottom is 34 Hertz. And then we induce some elliptic deformation at the bottom of the trap by playing with the radio frequency polarization. So we deform a little bit this disk into an ellipse. We rotate the main axis x prime, y prime at the frequency omega rod for some time. And then we go back to the rotationally invariant trap. And so depending how strong we do that, how long we do that, we can go up to this dynamical ring or simply have a vortex lattice at the bottom. And so if we rotate at moderate frequency, so this is 20 hertz, that is much less than our trapping frequency, we have, as you see, a very nice, I don't know if you see well, because here the contrast is not wonderful, but we have a very nice vortex lattice. And the dashed line, the blue line around, corresponds to the Thomas Fermi radius. So we still have an overall global parabolic shape. But inside this parabolic shape, there are holes, which are the vortices. But the overall shape is still Thomas Fermi. And then when we rotate further, what you can immediately notice is that the Thomas Fermi radius is larger. So this is a direct effect of this centrifugal potential that will open the trap, and for the same atom number, you will have a larger disk of atoms. And in fact, if you look at the number of vortices, you also have more vortices. In fact, there is a formula that has been established by Feynman that gives you the number of the density of vortices you expect as a function of the rotation frequency. And it is a very simple expression. So the density of vortices is expected to be the mass times the rotation frequency divided by pi h bar. And so I will show you how we count vortices, and in fact, it agrees very well with this formula. Now, if we rotate further and further, so the Thomas Fermi radius is larger, there are more and more vortices, and at some point, you see that it becomes harder and harder to see the vortices. It seems to be a bit smeared out. And so the feeling we have with this quick first look is that the vortex lattice has melted, and that there are some phase fluctuations, and it's not very clear that they are staying at where they should be in a lattice. So what I will show you now is how to study this transition from a crystal to a liquid phase for the vortex lattice itself. So now my particles are not the atoms, they are the vortices. Okay? All right, so thermal melting in 2 dimensions, it is something that is very well known for the 70s or 80s, and which is described by a theory which is also written by Kosterlitz and Thouless, but other people. So Kosterlitz, Thouless, Haldane, Nelson, and Young. So it is almost impossible to pronounce the name of the theory. So it's, okay, let me try. KTHNY. Okay, I won't say it again. And so this theory involves 3 phases, not 2, but 3. Because basically, when you have melting, you expect to have the liquid phase and the crystal phase, but here you have an additional intermediate phase. So at low temperature, of course, you have the crystal. For the vortices, because we are in 2 dimensions there, the minimum of energy is obtained when you have the vortices on a triangular lattice. So this triangular lattice is called an Abrikosov lattice. And so this is what is represented here. Each vortex has 6 neighbors. And this is what minimizes the interaction also in a 2D Coulomb gas, for example. And so below a first critical temperature, we have a crystalline phase, which preserves both translational order and orientational order. So I will come back to what I mean by that, but essentially, if I make a translation in the lattice, I see the same landscape. And if I look in terms of orientation of the crystal, because I could take this lattice and rotate a little bit, then it is another orientation. But here, the orientation here is the same as the orientation there. Okay? So both orders are there. And each particle has 6 neighbors. So now when I increase the temperature, the first thing that happens is that there will be dislocations that appear. And these dislocations will break the translational order. So what is a dislocation? A dislocation is a pair of 2 defects that you obtain by not by something very strong, but just by moving a little bit the position of two vortices. So if one is moved a little bit to the top and the other one to the bottom, now you see that this green guy here only has 5 nearest neighbors. So these 5 here. But this orange guy has 7 nearest neighbors. 1, 2, 3, 4, 5, 6, 7. And so this pair of two defects, 5 neighbors, 7 neighbors, is called a dislocation. And originally, the dislocation, they even appear in general by pairs of dislocation, because to have this, you really need to move very little some vortex lattices. And so this does not change the orientational order, because you still have basically the lines which far away are parallel to each other. But it breaks the translational order, because if you look on this side or on that side, what has happened is that there has been a pi phase shift between the two parallel lines, like that. And so in this situation, the translational order is lost, but there is still some orientational order. And so above a second temperature T2, what's happening is that the dislocation, they break into disclinations. And disclinations are isolated defects with either 5 or 7 neighbors. And here you see that it takes some time to recover from these 5 neighbor defects, or from this one has 7, sorry, and this one has 5. And by doing that, we also have lost the orientational order. Now it's not even parallel, the lines. So these ones are horizontal, these ones are tilted. So we also have lost the orientational order above this second temperature. So this microscopic mechanism is apparented to the Kosterlitz-Sarlitz mechanism of the BKT transition, in the sense that this happens when you break pairs, this pair of 2, 7, and 5, which constitute a dislocation to make a disclination. A little bit like in the story of the BKT transition, when you have pairs of plus and minus vortices that you break for reaching the thermal state, and the proliferation of 3 vortices is analogous to the proliferation here of these 3 defects. Right, so in fact, this physics is very general, of course, and it is not limited to quantum vortices. It's even present in classical physics, and it has been very well studied in systems of colloids, so little spheres in water. And people studying this system have seen very nicely this KTH-NY transition. This is also present in vortices in superconductors, and in our experiment, we study it in quantum vortices in quantum gases. So our approach is to look not at the transition by increasing the temperature, which for experimental reasons is not very practical in our situations, but instead to look at this transition by increasing the rotation frequency. Excuse me. And so this is more or less equivalent, because when we rotate faster and faster, what is happening is that we open the trap because of the centrifugal force. So all relevant energies, they go down. So if the temperature is fixed, with respect to the fixed temperature, my natural energy scale is lower and lower. And with respect to this natural energy scale, the temperature is relatively higher and higher. So we characterize where we're in temperature by looking at the ratio between the temperature, which stays fixed, and the critical temperature for the BKT transition in the trap that is opened by the centrifugal force. So this TC depends on omega, because when we lower everything, the critical temperature decreases. And so we look at the transition as a function of this parameter 2. Okay? right, so now let's look at the results. And to analyze the results, we need to look specifically at the orientational order and at the translational order. So we need to characterize it a bit quantitatively. And how can we do that? Well, the translational order is characterized by the pair correlation function. So I already introduced this pair correlation function yesterday in the lecture about BKT, when I mentioned that the group in Seoul, the group of Young and Shin, used it to check if indeed there were pairs of vortices, plus minus vortices, and what were their distance as a function of the temperature. You remember that? And so the way it is computed is you give me a distance, and now I count in the lattice how many pairs I have with this distance. And so, of course, if I choose a distance which corresponds to the period of the lattice, I will find many vortices split by this distance. So there will be a big peak. But also, if I choose a distance which is this distance, for example, or twice the period, or this distance. So there will be peaks each time I find distance that corresponds to some natural distance in a triangular lattice, if the atoms are well ordered. If they are not well ordered, this will be smeared out because I will have more or less any possible distance if everyone is moved a little bit. So I expect to have some oscillations if I have a crystalline phase, and something much broader if the phase is liquid. And in fact, this function we renormalize by a function that I would get if the vortices were completely uniformly spread. Because my gas is not homogeneous. It is with a Thomas Fermi profile and with a limited size. So of course, for example, if I take a distance which is larger than 2 times the radius, I must find 0 because there is nobody there. And so even if I take a distance which is close to 2r, I have much less possibilities to make pairs. So the number of pairs that I can do is also some function that I can compute mathematically, and I use it to renormalize the pair correlation function. The second function I will use is the orientational correlation function. So this one should tell me if the positions of the vortices, of the neighbors of a given vortices, are all along the same eigenaxis of my network, or if they are a little bit tilted in direction. So to do that, I introduce another parameter, psi k. I put a number 6 because it's with 6 neighbors. K corresponds to the vortex I am looking at. So for each vortex, what I am doing is to take the sum of e to the 6i theta kj, where theta kj is the angle between a fixed direction, so let's say the horizontal direction, and the next neighbor j. And I make the sum for all the neighbors. So the normal situation is that I have 6 neighbors, and that the angle between a fixed direction and each of these neighbors is sum of set plus n times 2 pi over 6. And so if this angle here is sum of set plus an integer number of 2 pi over 6, when I multiply by 6, I have an integer number of 2 pi. Okay, exponential I, an integer number of 2 pi, gives me 1. So I am left with e to the I, this offset angle for everyone, for all the 6 neighbors. And so I make the sum. I find 6 times e to the I, this small angle. I divide by 6, and I should find a complex number of modulus 1. So if the lattice is fully ordered, this has modulus 1. And when I take the average with all possible pairs of vortices which are split by a distance r. This should always be numbers of modulus 1 with the right orientation, because it should be always the same angle. So I take the psi star and the psi, so they should cancel also with this angle. And I should find 1 here, and the average should be 1. Now, if there are not 6 numbers, but 7 or 5, or if the angle like here is not split by 2 pi over 6, this will not be a complex number with modulus 1, but the modulus will be less. And then when I take the average, it will be less than 1. So what I expect, again, is that this function will oscillate, but will have some envelope that is 1 in a lattice, and then decays if I lose the orientational order. All right, so this is what is predicted by KTNHY theory. At 0 temperature and to temperature T1, we should have a crystal. And so in this case, already the pair correlation function decays algebraically, whereas the orientational correlation function should be constant. So this is the sign that, as I told you, there is no long-range order in 2D. So don't have too much hope. You will not find one for all correlation functions. The pair correlation function will decay, but very slowly, with only an exponent. It will only be an algebraic decay. Above the temperature T1, you have this hexatic phase, where you have lost the translational order. So now the pair correlation decays exponentially. But there is still some orientational order, in the sense that the orientational correlation function decays only algebraically. And finally, in the liquid phase, above T2, so both correlation functions decay exponentially, and you have lost both orders. So now you see that to compute these functions and to study them, I need to find exactly where are all the vortices in the sample to be able to compute all that. And so we need to implement some technique, automatic technique, if possible, because when you have hundreds of pictures, okay, I don't have so many PhD students to count all the vortices. So this you should do automatically. And so for that, we have an automatic procedure to count the vortices. So this is quite simple. So these are the raw pictures I have shown you before. What you do is you first filter to remove the high-frequency noise, and you get this kind of picture. So the filtering you should use is adapted to your optical resolution, because it's no way, you will not learn anything having pixels smaller than your optical resolution anyway, so you do that. And then from this smoothened image, you compute the Laplacian of the picture. So the Laplacian is a second derivative. A vortex here in this picture corresponds to a minimum of density. So the minimum of density, like a harmonic trap, has a curvature upwards. So the Laplacian of the density at that point, it has a maximum, because you have a peak in the Laplacian. And so you identify all the maxima of the Laplacian, and with that, you are able to spot the positions of all the vertices. So this works very nicely, in the sense that when we rotate faster and faster, you see more vortices. And in fact, if you compute the vortex density, you recover the Feynman formula I introduced earlier. All right, so this is how it looks like when you rotate faster and faster. Thomas Fermi radius increases, and then there are more and more vortices, and there are more and more disordered. So we have taken hundreds of pictures and analyzed them, rank them by rotation frequency, compute the pair correlation function, and the orientational correlation function and try to identify some behavior of a phase transition. So this is the result. First, for the pair correlation function. So something we do also, once we have identified the position of the vertices, is to construct the Delaunay triangulation. So this procedure identifies how many neighbors have each vertices. So the blue dots in these pictures are the vertices which have 6 nearest neighbors. The pink ones are the vertices which have 5, and the red ones have 7. So you already see in these kind of pictures that this picture seems to be relatively well organized. But here you see this guy here. It's a pair of dislocations, as I showed you before. And so then the calculation of the pair correlation function for this picture is given here. So as I said, we see peaks at the period of the vertex lattice, twice this one, etc., etc. And we renormalize that with the probability, the same function for a uniform case. And so at the end, we have these pictures. So this blue one is this blue one, and it corresponds to a low temperature. So we have nice, well-visible peaks at low effective temperature, so low rotation. And when we increase the rotation, the contrast of these peaks decreases up to some point where we barely have any oscillation. So this kind of feature is really typical for a solid to liquid phase transition. So from all these curves, what we extract is a decay length for the pair correlation function. So what we do is we fit with an oscillatory function and an exponential damping, and we extract a length Lg. We also compute the orientational correlation function. So as you see, the signal to noise is not absolutely wonderful, but still we can extract a typical decay. However, it's really hard to pretend that the data are decaying more exponentially or more algebraically, also because we don't have a lot of decays to identify which function it is. And when we try, in fact, both fits, they can do the job. And so we decided to fit everything with exponential to extract, again, one length that we can compare to the size of the sample, which is given by the Thomas Fermi radius. So now we have two lengths, the decay length for the pair correlation function and the decay length for the orientational correlation function. And of course, we want to compare them with the size of the sample to see if they are as large at the size of the sample, which means that the order is preserved, or if they are smaller, which means that we have lost the order and that we are above the critical temperature. Here is the result. First thing I would like to comment is this dashed line here. So this is the Thomas Fermi radius. And as I showed you already, the Thomas Fermi radius increases because here it is plotted in units of the rotation frequency. So when we rotate more, the cloud broadens. So I have two scales here. Here it is in rotation frequency, and here it is in reduced temperature, count in terms of real temperature divided by BKT critical temperature. So what we can see that at the lowest rotation frequency that we have investigated, the length, the decay length of the orientational correlation function is equal to the Thomas Fermi radius. So we do have long-range order for the orientational correlation function. However, the correlation function decay length for the pair correlation is below the size of the sample. So in fact, it's the phase we start in is more hexatic than crystalline. And in fact, it's quite difficult to reach the crystalline phase because here the temperature in the sample is 18 nanokelvin, so it's not like it's very hot. Okay. But still, at this temperature, there are already some defects in the lattice.
But then that explains why you couldn't do the fixed step, right?
Not only because this LG here, on the other hand, should be decaying algebraically in this region. But it's a question of signal to noise. And also something I would like to point is that we only consider rotation frequency above 0.7 of the trapping frequency. And this is because to make some analysis, we need to have a minimum number of vortices. Otherwise, you cannot do any statistics. If there are too few, of course, they cannot be ordered in a lattice. If you have 4 vortices, it's not relevant to speak of a lattice. So you need to rotate at some minimum frequency. And so that's why we cannot explore what is going to the left of this point, because then there are not enough vortices. Too many finite size system effects. So now when we increase the rotation frequency, what we see is that the orientational correlation length decays, and the pair correlation length also decays and become much smaller than the Thomas Fermi radius, and this corresponds to the liquid phase. So this is a first observation. When you see this data, you can see, okay, it seems that here the phase is exatic, here it is liquid. It changes somewhere in between. Not very clear. I would not bet exactly what is the value, but it's in this range, between these 2 points, that the phase transition occurs. And to check that this is consistent with the microscopic mechanism I have explained before, with this dislocation and this 5 and 7, we also have counted the number of defects in the samples. And these are 2 examples of the kind of lattices we see. This dashed line corresponds to the critical rotation frequency that I pointed in the previous slide. This dashed line here corresponds to this picture, so on the side where it should be exatic. And this red line, this is this picture where we expect it to be liquid. And you see directly that there are much more defects here than there. So first, there are much more vortices because we rotate faster, okay? But there are also much more defects. And here, the defects are a little bit more like pairwise. You see there is, again, this red, magenta, magenta, red configuration with a pair of dislocations. Whereas here, it's a bit a mess with many reds. And so here is the observation. So this 0.7 is what I told you. To the left of this point, it's also a bit a mess. The fraction of sites with 6 neighbors is rather low, but that's more because it's a small lattice, and so there are edges, and so it's not very relevant. So here is the central region where we can trust the statistics. So we have a majority of sites with 6 neighbors, and some 5 and 7, but very small. And then at some point, the number of sites with 6 decreases, and the others increase. And these ones are the ones which are neither 5, nor 6, nor 7, something else, okay? And so this counting is in agreement with what we observe also for the correlation function, and it also goes in the direction of this mechanism of dislocations. Okay, so to try to be a little bit more quantitative, because in fact the temperature we observed is rather low with respect to some upper bound that was predicted 15 years ago by Gifford and Baim. So they made a prediction, but their prediction for the upper bound is really a very large upper bound, let's say. But their theory is uniform. It's not in a trap. And so we decided to make some numerical simulations of the samples at finite temperature using the stochastic projected Gross-Pitevsky equation So this is probably one step further of what you have seen with Johannes. And this has been done in collaboration with USP. And we had a student from Monica Caracanias, Salvio Beretta, who visited us for 6 months and conducted these numerical simulations under the supervision of Romain Dubessy. And so this is one example of something that he simulated, you see, with just one defect in the center, so almost crystalline. And what he has observed is rather in agreement with what we have found in the experiment, and not in agreement with the initial prediction. So he does observe the crystalline phase where both correlation function, so the pair correlation function and the orientational correlation function are large. So this is the size of the sample. In his numerical experiment, he is able to tune the temperature. That's nice. And so when the temperature is increased, you have the exotic phase where the pair correlation function decays. And then after a while, you also have the liquid phase. And the critical temperature he finds seems to be in agreement with our data. Even it's a bit difficult to really put the number of atoms we have in the experiment. He has to work with a smaller number of atoms. And we are still working on it, so we are finishing this work now. OK, so this is my summary. I'm done, basically. I have shown you that we are able, in this kind of bubble traps, to access very fast rotation regimes and produce nice vortex lattices and identify their defects. Observe the thermal melting of the vortex lattice, which agrees with the 2D theory of Kosalis, Tholes, Haldane, Nelson, and Young. And in the outlooks, I would like to mention the look for defect pairing more systematically, these 5-7 pairs, etc. A quantitative comparison to a numerical simulation at finite temperature. And maybe explore if the fact that we are not in a flat trap, but in a curved trap plays any role. So what's happening when I increase the effect of the curvature in the trap? Does that influence this mechanism of this 2D melting? And so I will finish by thanking the group, and in particular the people who have contributed to this work. So David Ray was a PhD student on the experiment a couple of years ago. Rishabh Sharma defended in January, and he visited IFSC in San Carlos. So Salvio came for 6 months from San Carlos also. Romain Dubessy has led this experiment. He's now in Marseille, in France. Laurent Longchambon is an assistant professor in the group, and he has followed the experiment quite closely. Hélène Perrin is a CNRS researcher in the group, and Thomas Badre is also helping a lot on the experiment. And as I said, we have a strong collaboration with the group in San Carlos at USP, and where I was last week, in fact, before coming to the school, and I hope to come soon back. And so I thank you for your attention, and if you are interested in having some stay in France in our group, we are Brazilian friendly in general. So that's it. Thank you. So as it was seminar-like, you may have kept your questions for the end, so you can ask some, yeah.
I have a very small question. When you are counting these vortices, you still consider the edges?
No.
No, you don't consider it?
No.
Okay, that was my question.
Yeah, this is an important question. So in fact, we remove, we count the vortices in a circle which is about 0.8 of the Thomas Fermi radius. Otherwise, we will have many effects that are there just because, okay, that's the end of the sample, and on the border, they cannot have 6 neighbors. So this is a very relevant question. I should have said it directly, but yes. Yes? To have access to the crystalline phase? Yes. In fact, from the numerical simulations, it seems to be relatively hard, at least in the oblate trap, as we have. And it is a little bit linked to the geometry. In fact, in the... so maybe I have... yeah. So this graph here is a theory I was mentioning by Gifford and Bile that predict an upper bound for the melting transition. And at the time when they did this work, there was a very strong experiment by Eric Cornell on vortex rotation. And he was able to have very nice vortex lattices. And they plug their experimental parameters in the model to identify what was the melting transition for their situation. And Eric Cornell has a trap which is more cigar-shaped than our trap, which is oblate. And in fact, this prediction for the melting temperature is much closer to the BEC critical temperature when you have a cigar-shaped trap than in the case of our oblate flat trap, where it drops and it is expected to be much less. It's even in the conclusion of the paper that maybe it's difficult to observe this melting transition in this cigar-shaped trap, because once you are condensed, almost immediately you have a crystalline phase. And indeed, if you look at the lattices that Eric was able to produce, they are very, very nice, very pure. And I'm not sure I have it on this series of slides. No, I removed it. Oh, yes, it's there. So here, what Eric was able to observe are Tkachenko modes, where you can have almost a perfect crystalline phase, and you can see the very, very low collective modes of this phase, which are deformation, long wave deformation of the position of the vortices. So this is the first mode. This is the second mode. You see there are tiny waves on the axis along which the vortices are. And this he can see because it starts from a cigar-shaped trap. So this is possible in some trap geometries, but with our oblate traps, it's really, really difficult. You have to go to much lower temperatures. But this is a very relevant question. No more questions? Okay. Thank you very much. And I would also like to really join what Mathilde said earlier, to thank the organizer and also thank to Mathilde. I mean, you are among the organizers. Because it was... yeah, you see. And so I really enjoyed very much being there, even if it was a lot of work to prepare the lecture. I hope it was useful. And okay, I don't promise proper lecture notes, but I will maybe negotiate with one of the students who has taken really nice notes to share them with you. And I will give you access to the slides at least, but the notes are basically my notebook, bad handwriting. So, okay, if you give me some time, maybe I give you something, but I will do my best.